Welcome back, ladies and gentlemen. Today, we're going to be talking about intermolecular forces and the bonding between atoms. We already know a lot about this. We know about ionic bonding, we know about covalent bonding, we know about the whole give and take, we know about the sharing, but there's more to it. Physical properties is sort of an introduction to physical chemistry, where we talk about the physics behind the chemistry. Why do things work the way they do? Why don't they do something different? Why do these elements share? Why do these elements give? We just told you in grade 10 that they did, and you went, okay, sure, whatever. Well, there's a reason why they do. It's called electronegativity. Whoo, big word. Break it down. Electro, come on, that's an electron. Negativity, it's negative. The negative electron. Again, with the scientists naming things. Previously, we said that elements in families like halogens wanted electrons. But just because you're hungry doesn't mean that you get to eat. An atom's ability to pull on electrons is called its electronegativity. So the halogens want electrons, but, you guys want a passing grade. Whether or not you get one will depend on how well you work, obviously. So the higher the electronegativity of an atom, the more it attracts electrons. So for example, fluorine here pulls with a strength of 4. That's a very strong pull. Hydrogen pulls with a 2.1. That's a little bit more moderate. Now, in your notes, you guys have a copy of this book in your booklets, but the problem is that it's black and white. So here it is in color, very useful in color, unfortunately. The table referenced below, the next slide, is a table of electronegative values. These values are useful in calculating whether a bond is called a polar bond or a non-polar bond or an ionic bond. We'll talk about that in a second. But here it is. What are we looking at? The bigger the electronegativity, the more that element will pull to get electrons. So fluorine right here and oxygen and chlorine underneath it, those guys are really, really red, right? They're really, really electronegative. They're basically big, strong bullies. Everyone else near them are less strong. And down over here, you'll see these guys are not very strong at all. They barely have a hold on their electrons, which means it's very easy for someone to steal them. Interesting. Now, these numbers, you might ask, do I have to memorize these numbers? No, you don't have to memorize the numbers. What are these numbers from? Complicated. I mean, the biggest number here is 4, and the smallest number is 0.7. So it's not a simple calculation that resulted in this, but it's the combination of work of many, many scientists over a long time. You'll also notice some unusual quirks, like, for example, the halogens, of course, have, not the halogens, the noble gases have no electronegativity, except xenon for some reason. Xenon does a weird thing. Similar, we don't have much information about the lower parts of the periodic table because most of these guys are radioactive and do other weird things, so every time we try to measure their electronegativity, we set off an atomic explosion. All right, that's a bit of an exaggeration, but the same basic idea. When we try to study these guys, it doesn't really work very well. So what does this turn into? When an atom wants an electron and pulls strongly, they have a high electronegativity. When the atom doesn't want an electron and pulls weakly, they have a low electronegativity. Electronegativity follows a trend if we look at the periodic table. If you move from left to right, electronegativity increases. As you move from the bottom to the top, it also increases. All right, so if we again go back here one slide, this is the smallest possible number, and as I go up this way, the numbers get bigger. Also, this is the biggest possible number. So the more I go towards the right, the bigger it gets, and the more I go up, the bigger it gets. Now, the reason behind this, I think I have that on the next slide, do I? Yes, I do. The electronegativity is made of 2 competing aspects for each atom. Number 1, how much the core pulls on an electron. Number 2, how much the shells push away a new electron. Wait, what? The shells? Why would they push away? Why do the cores pull? Okay, well, the core of an atom has protons, and protons are positive, and electrons are negative. And positive and negative attract each other. So it makes sense that the bigger the core, the more pull you get. What do the shells do? Well, the shells are full of electrons. Like, look at this guy over here. That's a lot of electrons. So when a new electron is trying to come in and say, visit, right, I got a new electron here, and that new electron is sitting right here, and it's like, hey guys, I want to come visit. Is that okay? And all of these other electrons just shout at the same time, no, get out. Compare that to over here. A new electron shows up, and there's just 3 other electrons, and those 3 other electrons are like, get out of here. Get out of here. Why are you staying here? No, get out. Get out. Ah, jerk is sticking around. So the more shells there are, the more other electrons there are to jealously push the new one away. The less of them, the harder it is for those electrons to gang up on the new guy. The core is going to pull either way, but the question is this tug of war. Who's winning? The core's pull or the shell's push? And of course, the further away the outside shell is from the core, the weaker the core is. Right? So like in this case here, the new electron's coming in, and those 3 protons in the middle are going like, yeah, come on down, more of the party. It's great when more people come to visit. These 3 are busy yelling, go away, we don't like you. But the electron coming in can still hear the protons in the center. They can still get the welcome message. Compare that over here. The one electron that's coming in is trying to get close. The core is like, yeah, totally come join us. It's fine. It's a great party. We really want you to be here. Meanwhile, all the other electrons around the shell are all shouting much louder. They're drowning the guy out. So think about that, right? The number of shells increases based on your position on the table. Lower down, right, every period, every row adds a shell. And what do we see? As we go down, the number of electrons increases, and they start to win the tug of war. They start to push the new electrons away. And that's what we get going down. What does it matter going left and right? As we go more and more right, the electrons in the protons in the core, there are more of them, right? Here, there's going to be 7 protons. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 protons. I can count. There are 9 protons in the core. Those 9 protons have got a lot of pull. And there's not very many electrons, not compared to what there would be lower down. So those protons have got the maximum possible megaphone, right? Their pull, their voice is as strong as possible, and the opposition, the shells, the electrons are as weak as possible, relatively speaking. So what happens? You get a very strong pull here, you get a very weak pull down here, because down here you've got not as many protons as you'd like. You get more on the other end of the table, and you've got lots and lots of shells between the protons trying to get their message out and the new guy coming in. So, big pull, small push, medium pull, medium push, small pull, big push. The difference in the electronegativity between 2 atoms determines what kind of bonding we get. If you have a moderate small difference, you get covalent bonding. If you have a fairly large distance, you get an ionic bond. And again, we know this. We've talked about this before, right? If the 2 of them, we talked about it when we talked about covalent, and we said, look, if the 2 of them are going to share, right, what's going to happen is that both of them are going to grab on, and they're both going to try to pull. But if they both pull about the same, nothing happens. But if one of them is like, give me that, hurrah, then obviously we're going to get ionic because we get a transfer of electrons. So that first picture with the 2 people sitting down, the 2 atoms sitting down enjoying a meal, over here sharing so nicely, this one donating a ring, so generous. Yeah, it's a little bit more like a cage match where everyone's trying to fight each other to take the best. So it's a little less kind, it's a little more vicious. But, chemistry, who says it can't be exciting? Previously, we treated these types of bonds as 2 separate things, but they're actually part of what is called a continuum, or a range of values. It's kind of like a rainbow, right? Because it's not so much that one of them is strong, one of them is weak. They're differing levels of strong and weak. Which one's the strongest? Which one's the weakest? Depends on the context. Fluorine's really strong. Fluorine with anything, fluorine's going to win. But what about like chlorine and oxygen? They're not as strong as fluorine, but if they're on their own with anybody else, they'd win, right? So it depends on the dance partners that we've got. So this is kind of what we're dealing with when we're talking about bond types, right? There's covalent on that end of the spectrum, and there's ionic on this end of the spectrum. And the closer you are to the right, the more ionic you are. So like way over here on the far right side off screen with me, that'd be your like fluorine lithium bond or fluorine hydrogen bond. That's the hydrogens coming by and it's just like, I got a nice electron, I really like my electron, electrons are cool, and then fluorine just shows up and like clocks him in the face and takes the electron and is like, this is mine now. That would be your extreme ionic. Covalent on the other end, this is your like big time sharing. So like way over here, you're going to get two oxygens who are basically perfectly balanced in how much they hold on to this thing, each one pulling an equal amount. But then you got this area in the middle where different things can happen. Now you'll notice I put a little dividing line there. I'm saying that's the divide between ionic and covalent. It's pretty arbitrary, really. We kind of decide where the boundary goes based on what we are noticing as properties, right? So like everything on this side of the line behaves ionically. Everything on this side of the line behaves covalently, but the stuff in this sort of green to yellow zone is going to behave a little differently. Because it turns out that there are two broad options for covalent bonds. You got your non-polar bonds and your polar bonds. What in the world does that mean? Well, let's think about what the word polar means, because obviously there's option 1 and option not 1, because it's non-polar. So bond polarity, what does that mean? When a bond is formed, the electrons will move. For ionic bonds, the electron is fully transferred, making one side positive and one side negative, right? That's our punch-out fluorine who shows up and takes the electron. Covalent bonds, the electron is shared, but they're not always shared equally. The electronegativity of an atom tells us how hard it pulls on the shared electron. Like a tug-of-war, the bigger pull gets the electron most of the time. Or the usual example I give, it's like that friend of yours who shares your pizza and somehow eats most of it. You know, hey, can I have a bite of that? And then they like eat half the slice and you're like, thanks dude, that was my lunch. High electronegativity, or in this case, a high hunger. So we call an electron shared equally non-polar. So if it is perfectly equally shared, it is non-polar. And if we take a look back at the little picture here, I said that perfectly shared oxygen is on this end. It's non-polar. This end is not evenly shared. One of the two of them is a bit greedy. One of the two of them is taking more than they're giving, much like an ionic bond, but not fully. They're still sharing it. It's just not doing a very nice job of it. So, there's one more there. We call an electron not shared equally polar. Now, where's this polar stuff coming from? Hydrochloric acid. This is considered polar because it looks something like this. Whoa, lots of stuff to see. Okay, so we got hydrogen and chlorine. They're sharing electrons. You can still see the electron dots there. This yellow electron right here, that's the one that hydrogen brought to the table. But what we're seeing is that the chlorine's pretty greedy. Remember, it was about a 3.5, I think? No, it was a 3 on the electronegativity. So it's grabbing a hold of those electrons and it's just pulling them over. And it's like, hey, hydrogen, thanks for bringing some food to the party, but I'm really hungry, so I'm just gonna sit with the bowl of chips. I'm just gonna keep eating them. And then hydrogen occasionally comes over and is like, can I have a chip? And chlorine's like, yeah, I guess. Okay, here you go. Yeah, sure. You know, hey, thanks for bringing it, though, but they're mostly mine. The way we show this is that we sort of draw this bulging cloud, right? This shows over here, this blue side, this area that's larger shows where most of the electrons are, whereas this side here has got less electrons. There's also some weird symbols here. We'll talk about those in a second. Chlorine gas by itself, just two chlorines, are nonpolar. So what we see here is that this has a cloud that's a lot more uniform, a lot more even, a lot more the same, right? So both of them brought the electron to the table, and they're sort of like, look, I don't like you, and you don't like me, but we need to share, okay? And they're like, all right, fine, we'll share. And they share perfectly evenly because they're kind of a little bit aggressive like that. So here's our nonpolar example. Here's our polar example. Right? And it all comes down to how the sharing is working. Right? So now we have a word to describe how well the electrons are being shared. If they're shared a lot, right? If they're shared very evenly, non-polar. If they're not shared very much at all, but instead one guy's kind of taking it all the time, we call that polar. So bonding, we've broken it down in grade 10 into covalent and ionic. But now we're going to break it down further, right? We're going to say that covalent has two options as well. There's polar and non-polar. And these are the different images that we could have for them, right? A non-polar bond is very even. A polar bond is a little bit more extreme. An ionic bond is full-on extreme. It's a full transfer. So one of them becomes positive and one of them becomes negative all the way. Another way to sort of look at it here, non-polar bonds. Okay, well, I don't want to go to that. Let's talk about that symbol that we saw. I thought I had a slide for it, but here we go. So this symbol here is a lowercase delta. It's a Greek letter. So uppercase delta is that triangle. The lowercase is sort of like this kind of thing. All right? Now, the delta is used in this case, the lowercase delta is used to represent a partial charge, like a half charge. They're not really half charges, but what we're basically saying is, look, these guys share perfectly evenly. These guys, not so much. These guys are sort of one side's being a little bit more greedy. So this side over here has got more electrons, so it's a little bit more negative than this side over here. This side is more positive. That's all they're trying to say. So they're just using this sort of symbol to represent the fact that it's not fully positive or negative. It's partially positive or negative. Why did they use a Greek letter? Scientists are nerds, in case you didn't know that. And a lot of those nerds in the old days used to also know Greek, so they thought, well, I'll just use my nerd language. That's not totally the only reason, but, you know, also Greek's a pretty good language, to be honest. Anyway, so for non-polar compounds, there are kind of two options here. Right? I said that they share equally, and we talked about chlorine sharing equally. Chlorine shares equally, it makes sense, right? As I said, look, I don't like you, you don't like me, but we're both equally strong, so if we try to fight over this electron, it's not going to get anywhere. Let's just work together. What's happening is there's other options, though. There's symmetry by number. That's the first option that we just talked about, where the electronegativities are exactly the same. So the two of them are like, for example, oxygen or the chlorine, right? The two of them are equally strong, so they can't overpower each other. It'll always be exactly the same. But there's another option, symmetry by geometry, where the shape of the molecule balances the pull. Wait, what? What do I mean by that? Look at this guy. You got good old carbon dioxide there, the stuff you're breathing out right now. Carbon in the middle doesn't have a very strong electronegativity. So by itself, right, if there was just carbon with no other oxygen, so if it was just this, carbon monoxide, this oxygen would pull way stronger than this carbon. So the electron would be hanging out over here with this oxygen, and this would be a polar bond. But there are two oxygens here. So it's almost like, you know, the first oxygen came in and is like, carbon, my friend, you need to give me your electrons. And carbon's like, well, I guess so. I guess I can share. And they start handing them over, and then another oxygen shows up on the other side and is like, whoa, carbon, what are you giving him the electrons? I should get some of those electrons. And then the two of them basically grab onto carbon on both sides, and they pull. But because both of them are equally strong, they both pull the same. So the electrons end up being pretty even. Because, you know, once this guy over here grabs one electron and tries to pull it this way, well, the other guy grabs another electron and pulls it that way. So everything balances out, and this becomes non-polar, even though carbon himself isn't very strong. The other way you could turn this whole thing around, right, and explain all of this a little bit better, carbon tricked the two of them. There we go. Now it's less about carbon being the victim. Carbon tricked the two of them. The carbon's like, look, I can't beat both of you, but if I make the two of them fight each other, I win out on top in the end because I'm still going to be in the middle okay. So these are the two sort of big options about how we can get a non-polar bond, right? If the two of them are perfectly balanced, or if two opponents perfectly balance themselves. In both cases, the electrons are pulled evenly in all directions, so no one will win that tug of war. You are not expected to know the shape of molecules before anyone panics. Like, whoa, carbon dioxide looks like that? I had no idea. That's a university level thing. You would go into that in a lot more detail later on in your career. But if I showed you some atoms, you should be able to tell me if they're symmetric or not, right? Like, you should be able to look at that and tell me, oh, that's a perfect line. Oh, this is a perfect line. I think I can figure that out. Just be aware that if something is symmetric, it is non-polar. That's the key thing I want you to pick up on here, okay? So, as we said, we got types of bonding. We've got covalent, we've got ionic, we've got our polar and non-polar, as we mentioned. And non-polar is broken down by symmetric by number, the two of them pull equally, or symmetric by geometry, where the shape is balancing out the pull. So over here we see our ionic, we see our polar compounds, and down here we see our different symmetry compounds. So this one here is symmetric by number, this one here is symmetric by geometry. The two guys on either side each pull evenly. That's a lot of stuff, especially given that up until grade 10 we were just here at ionic covalent. But it's not too bad, right? Like, both of these are symmetric, that's the key. So if it's symmetric by either number or shape, it's nonpolar. If it's polar, it's not symmetric. That's the only thing we need to really keep track of. Another way to look at it, there's our ionic, right? We got a dog with a bone. The two of them get in a fight, and the bigger dog gets the other bone. And then, since they're both positive and negative, they attract. Then you got this one. Well, the first dog couldn't pull it away completely, but the big dog over there on the right is stronger than the one on the left, so you end up more or less being pulled to the right. Finally, got our last option, where the two of them are equally strong, so this is symmetric by number, and they both share evenly in the middle. So there we go. This is the basis of these types of bonding. So now, you guys have a little bit of an exercise you can try. Try balancing out, seeing if you can identify from a series of pictures which compounds are polar, which ones are non-polar. Now, once again, the downside is your book is black and white, not in color. So certain questions are going to be a little harder to do. I recommend taking a look at the color version online, because the color version is going to be pretty significant. But other than that, I'm going to leave you guys here, and next time we're going to talk about intramolecular forces. That sounds almost like the same word, Mr. C, and this was already complicated. I know, but that's why we're breaking it down step by step. Okay? All right, guys. Next time.